Okay, this is my presentation from me, Adam, and Johnny on the materials and the products we selected. So, summary: the objective of this report is to test 3 different materials, which were polypropylene, polyethylene, and polycarbonate, to conduct a hardness test and gather each polymer's monomer structure, chemical composition, and other characteristics specific to the polymer, i.e., tensile strength, physical properties, and chemical stability. That's the contents of what's going to be in this report. So, the aims and objectives you can see there. Introduction: polymers are made by adding monomers together. Monomers are the individual molecules that, when repeated in chain, produce what is known as a polymer. The backbone of a polymer is carbon, so they are known as organic. Polymers are lightweight, disposable, poor conductors of electricity and heat, are useful at low temperatures. Polymers can have a high molar mass that can consist of 100,000 molecules. There's 2 types, homopolymer and copolymer. You can see the difference between them there, and you can see the categories of the plastics. Here's a few more information about different types of plastics. Obviously 2 types of polymers, thermoplastics and thermosetting. You can see the difference between the 2 of them there. So the product I looked at was a Ferrier Washington liquid bottle, which was made of polyethylene, high density polyethylene and low density polyethylene. Lid for the high density, bottle for the low. As you can see, they both share the same chemical structure. There's a picture of the chemical structure, and there's the model that we made of the actual structure. Below you can see the 2 materials for each part, their chemical structure, and the short hardness test results we got for 3 different tests. Low density polyethylene is a homopolyethylene with a long chain branch structure, branch approximately 2% of carbon atoms. Branches disrupt and reduce crystallinity compared to HDP, resulting in a more flexible but lower strength material with slightly lower density, generally used for chemically resistant fillings, as you can see from their different types. There's the different trade names it's used under: lupin, purell, pharmaline, and ribylene. So there you can see the mechanical and physical properties of polyethylene. The strengths and disadvantages are very cheap, good chemical resistance, hydrolysis resistance, high impact resistance at low temperatures, good persistability, insoluble in organic solvents. Disadvantages: low tensile strength, high friction and poor wear property, poor UV resistance, dissolves in heat and burns very easily, will swell in alibatic and aromatic hydrocarbons. There you can see the 5 reasons the material was used. 3 other possible alternatives to polyethylene is soda borosilicate, glass, stainless steel, ferritic, and bamboo. So the first one was soda borosilicate glass. There you can see the statistics and the figures from it all, the tensile strength, chemical stability, and the processability. The reasons for: more durable than other forms of glass, widely used in the industrial industry, chemically stable, does not react with chemical substance, therefore great for use in cleaning products, etc. Recyclable, is able to be reused and recycled. Reasons against: expensive, more expensive than producing LDPE, and not flexible, which would be needed for a washing up liquid bottle. Second one was stainless steel, ferritic. You can see the statistics there, the price, the tensile strength, the chemical stability, and the processability. The reasons for: durable, strong material, does not shatter or break easily, chemically stable, resistant to corrosion from chemicals, recyclable, and reasons against: expensive due to machining and not malleable as other materials. Third one was bamboo. As you can see there, the statistics for them as well, the price, the tensile strength, chemical stability, and processability. Reasons for: cheap, it's organic, strong and flexible, and reasons against: chemically stability poor, unless it's treated it begins to deteriorate over time, and it's expensive to process regarding to making bottles.
Okay, so the product I've selected for this lab is a baby feeding bottle, in particular the main body of the feeding bottle. The chosen component for this product is the main body of the bottle, as I said, which is made from polypropylene and is free from bisphenol A, BPA, which is an organic synthetic compound which has been banned since 2012 over health concerns. Polypropylene is a thermoplastic addition polymer made from a combination of polyethylene monomers. It is used in a variety of applications, including packaging and consumer projects, various others, including baby products, such as the bottle chosen here. Here you can see the completed monomer, completed in class. Progression of the monomer build: 3 single carbon atoms with a single bond and a double bond shown here. The first carbon has an addition of 3 hydrogen atoms. The middle carbon has an addition of 1 hydrogen atom. And then the final double bonded carbon atom has an addition of 2 more hydrogen atoms, which gives it the molecular structure of C3H6. Characteristics of polypropylene can be seen here. Some examples are it's tough, rigid and lightweight material, good mechanical properties, good chemical resistance, makes good material for electrical insulators, it's non-hygroscopic. Typically polypropylene is susceptible to UV degradation, therefore outdoor use UV inhibitors or 2% carbon black are required for acceptable service life. Here are some trade names from some selected manufacturers used for polypropylene. Composition details, it's 100% polymer, it's in the plastic thermoplastic semi-crystalline family. Base material is polypropylene and core is PP. Properties of polypropylenes can be seen here. Tensile strength is 32 megapascals, flexor strength 41 megapascals, heat deflection temperature is 100 degrees. You can see some details there. Chemical resistance, melt temperature of 130 degrees, and transparency, again details can be seen here. Reasons why polypropylene is selected for this application, due to its high melting point of 130 degrees, makes polypropylene a good choice for this selected application. Good chemical resistance also, as harmful materials do not seep into the liquid. Non-hygroscopic, as I said before, durability and resistance to fatigue, and recyclability. Alternative materials selected for this. The first material was soda lime silica glass. Here is its composition detail. Some of its properties, such as tensile strength and flexor strength, which is similar to its tensile strength is similar to polypropylene. Reasons for: recyclable, transparent, cheap to manufacture, chemically stable, good chemical resistance, and it's time proven as glass balls have been used and manufactured for a long time. Reasons against: not resistant to high temperatures and sudden thermal changes, much heavier than polypropylene, can fracture or shatter very easily, which would be impractical for this application. Second alternative material is polyphenol sulfone. Its composition and its molecular structure can be seen here. Some properties again, you can see it's much higher tensile strength and flexor strength than polypropylene, and a much higher melting point. Reasons for: better durability and heat tolerance than polypropylene, does not absorb water, naturally BPA free, higher tensile strength than polypropylene. Reasons against: it's very expensive to produce, poor impact resistant, subject to stress cracking, low continuous service temperature. The third alternative was silicon carbide. Properties can be seen here. Again, much higher tensile strength and flexor strength. Reasons for: low thermal expansion, high thermal consistency, high hardness, high elastic modulus, excellent thermal shock resistance, and good chemical resistance. Reasons against: expensive to produce, manufacture, due to its extensive and complicated manufacturing techniques used. It also needs a thick layer crystalline structure. Toxic substances are produced and are used in the manufacturing.
Continuing on, the material I'm going to speak about is polycarbonate, PC. Polycarbonate is widely used thermoplastic. We can be seeing here that it's the pink section of the Colgate toothbrush which is being examined. It's used to manufacture electrical components, safety helmets, riot shields, and baby feeding bottles, amongst other things. Trade names and suppliers. Other trade names: polycarbonate, carbon acid, homopolymer, carbon acid polymers. Suppliers include Bosch, and Chemicava, a Chinese company, pharmaceutical company. Why it is used: characteristics: good optical transparency, strong, stiff, hard, remains rigid up to 140. It's excellent toughness, high thermal stability, high dimensional stability after moulding. Cons: limited chemical resistance, limited scratch resistance, yellows when exposed to UV. This can be reduced by introduction of black carbon additives. It can be formed via extrusion, vacuum forming, blow moulding, structural foam moulding, and injection moulding. Some of the properties can be seen: mechanical properties, thermal properties, and processing properties. Can be seen here. Other chemical properties: hot water causes gradual chemical decomposition, impact resistance to -40 degrees Celsius, has high melting viscosity, but it has very high CO2 permeability, so there's a necessity for barrier layers. Here's the molecular formation, can be seen here, using one method, which is bisbene produced into a sodium salt. Then it's reacted with phosphagen to give you your monomer of polycarbonate. Components: 5 reasons it was selected: it's tough, high wear resistance, easily machined, good mechanical, physical, chemical properties, no risk to human health. These are the exercises that were carried out in class. You can see the monomer is quite large compared to other polymers. And on the left here, you can see the SciFinder molecular structure, which was also found using the website. The monomer was created using Molymod set. Alternatives: here's a table of alternatives that could have been used. So a polymer that could have been used was CAP, cellulose acetate propionate. Pros for this: it's tough, easy processed, and good chemical stability. Cons: it has lower tensile strength than polycarbonate, it's more expensive, and it's harder to recycle. For a metal, aluminium could be used, which is becoming more popular. It has high corrosion resistance, it's recyclable, and it's non-toxic. However, it's expensive, requires higher temperatures to be molded, and can stain from water. A composite is polyether terpenton, I think, PEEK. Its high thermal resistance, can be blended with PESS. It's expensive, UV weathering and processing at high temperatures. Here's the procedure that was used and the SureD device. Here's the results that were taken from the Sure Hardness test. It can be seen here for each product and its materials. From the results, we can see that the high density polyethylene was the hardest of all polymers. For each polymer was coincided with its practical use. The specific details of each polymer has already been discussed by each individual in the group. Conclusion: to conclude, it was set out to investigate the molecular structure of 3 polymers. This was done by using SciFinder and EduPack programs, as well as the Molymod molecular sets for better understanding. The hardness of each material was done by using the Sure Hardness apparatus D. It was also set out to find alternative materials for each of the materials. This was done by searching for materials with similar mechanical, chemical, and physical properties on the above mentioned platforms for research. References to where all the information in today's presentation was found was EduPack and SciFinder respectively. That concludes the presentation. Thank you for watching.